Linear regression equation, a linear regression line. When you make a scatter plot, we made scatter plots the other day. So when you make that scatter plot, you're going to put the line on the graph of the scatter plot. And when you do that, that's called a regression line. Well, the absolute perfect line to fit the data is called a linear least squares regression line. So if you ever see LSRL, you're talking about a least squares regression line. So the line measures changes in x and y, and it's given by the equation y equals a plus bx. There's another lin reg, ax plus b. We don't use that one unless you go on to another class or another, like Hancock College uses ax plus b in statistics. Regression lines are used to make predictions. That's the goal. We want to say how accurate is our prediction. The slope of the line is the amount of increase or decrease for every 1 unit in x. So I'll talk about that with the manatee data. Hopefully you still have that in your calculator. Extrapolation is predicting outside the data set. Interpolation is predicting inside the data set. So if you extrapolate, you're going to make an inaccurate prediction. So those are predictions that are not very useful. And then we'll talk about residuals. One thing that's not on here is r squared. So we found r squared on our calculator. Is anybody still having a problem getting r and r squared on their calculator? I had office hours yesterday. I had a few people show up, and we talked about getting r and r squared on a calculator. All right, so this is the manatee data, and we've got to come up with an equation for the manatee data. Is the relationship linear? So that's the first question we're going to answer. Is data linear? So we have x, we have y. X is going to be powerboats. Y is going to be manatees. So we're going to make a predicted value. Ultimately, that's the goal. How accurate is our prediction? So first of all, is the relationship linear? We're going to make a scatter plot with our calculator. So if we still have the data. If you don't, then enter the data into list 1. So powerboats, x. We always want x to be list 1 and y to be list 2. So again, stat, enter. List 1 is all your x values, your 5x values. List 2 is your 5y values. Then zoom 9 will give you that graph. But you have to have your plot on. Press zoom 9 and you should see a scatter plot. So there's my scatter plot. 5 points. 5 points on the graph. Look kind of straight. Find the mean and standard deviation. So the way that we do that is we want the mean and standard deviation for each value. So there's 2 things that you want to do whenever you enter data into a calculator. You want to do linear regression, a plus bx. And you're going to enter list 1, comma, list 2. You don't have to put list 1, list 2. That's the default list. If you leave that blank, then it'll still find your a, b, r, and r squared. So when we do that, we got a is negative 42.1. Or actually, I'll just write the equation. So y hat equals negative 42.1 plus 0.133x. That's the regression equation. And then the other important values is r and r squared. R is 0.937. The next thing you want to do is lin reg a plus bx. That's number 8 on calc. And then calc number 2. So this is number 8. We also want to do number 2. Two variable statistics. And this will give us our statistics. We're going to do it on the next slide. We're going to write the regression equation. We're going to write the regression equation without coming up without the a and the b. So there's a way to write the regression equation with x bar, y bar, s of x, s of y. So if you do that, I would record that data as well. So I got x bar equals 506.4. Y bar equals 25. Sx. Standard deviation of x, 61.7. Standard deviation of y is 8.7. Alright. So we got the regression equation. We got the two variable statistics. So we got all the information about this. We got a scatter plot. Predict how many manatees there are when the x is equals to 34. If we do this, this is called extrapolation. Okay, if x is 34. So we don't want to extrapolate. If x is 34, we want to use a number like that's inside the data set. We want to interpolate. So we want to take a number like 447 or 460 or 481 or 500, 520. Those numbers are inside the data set. So we want to interpret numbers inside the data set. Predicting when x is 34,000, we're going to use the equation. The predicted value is negative 42.1 plus 0.133x. And I'm going to end up with a negative number, I know. Negative 42.1 plus 0.133. So this is making prediction for your equation of the line. Negative 37. Okay. If there's 34,000 powerboats, x is negative 37. If there's 0 powerboats, x is negative 42. Okay, negative 42 manatees killed. And that doesn't make any sense. We can't have negative numbers. The number of manatees is a positive number. So 34 doesn't make any sense because that's extrapolating. We need, like I said, we need a number inside the data set. So I want to use when x is 460. So let's see what that makes. 460. The actual value is 21. When I make this prediction, I get 19. So if y is 21, y hat, this is y hat. Let me use a better color. This is y hat. These are means, x bar and y bar. And this is y hat. Y hat means a predicted value. So I made a prediction. I predicted when x was 460, y hat is going to be 19. 19 manatees killed. That's predicted value. Let's interpret the slope of the line. So the slope of the line is going to be I'm going to write down here. The slope of the line B equals 0.133. Okay, so the slope of the line is rise over run. So B equals the slope. And we're going back to Algebra 1 to predict the slope of the line. So think rise over run. Or the y's over the x's. Y over x. The difference in the y's divided by the difference in the x's. So remember, we could do 481 minus 460, 24 minus 21, and divide those two numbers and come up with the slope of the line between the 2 points. But the B is the predicted, the average prediction. Okay? So we always want to have that word predicted value. So whenever you interpret the line, we're thinking predicted value. So I got the slope of the line is, I always write it out in terms of the numbers, 0.133 y, which is number of manatees killed. I'm not going to write the whole thing. Number of manatees killed, that's y, divided by x. That was terrible writing right there. And divided by x is 1. So it's per 1 unit. Okay. But in this case, these numbers are in thousands. 447 means 447,000. So I'm going to write it in thousands. Thousands of powerboats. Alright, so what does that mean? Rise over run. We're going to say for every 1,000 powerboats registered, we predict an increase. Okay, this is not a decrease. If it is negative, if B is negative, it's a decrease. An increase on average of 0.133 manatees killed. Alright. So that's interpreting the slope of the line. We'll get an opportunity to do that again a little bit later. Interpret the slope of the line. Another way to write that, you can write the x value last. So write the y value first and the x value last. For example, we predict an increase on average of 0.133 manatees killed per every 1,000 powerboats registered. And that's a little more direct because that's like writing miles per gallon or something like that. If you have miles per gallon, then you say the per second. I'm going to do this on the calculator, so I want to go, first of all, stat. Go stat, enter, and again, list 1. Highlight L1 and clear. To get rid of stuff in your list, we're going to clear list 1. Press clear. And then I'm going to enter the data into list 1. So I have 447, 460, 481, and list 2, 13, 21, 24, 34, and 33. Alright, second, y equals gives me a scatter plot, so I'm going to go turn it on. and then go to the first graph, which is scatter plot. Default L1 and L2 pops up, and these are your marks on the graph, so you can make plus signs if you want to. I like the plus signs. And then the color of your graph, and then always zoom number 9. Well, what happened there? I think I entered data wrong. Let me double check my data. Come on, graph. Okay, well, I got something in y equals. That's what's taking so long, is graphing y equals. I gotta clear that stuff. I got exponential stuff in y equals. That's what happened. Let me double check my data. Oh, I put 85 instead of 585. I knew it was off. It should be somewhat linear, or usually when you make a graph, you want to check that. So I knew I was going to be off by a little bit. All that stuff. So my plot is on. I'm in the plot screen, and then I press zoom number 9. Number 9 is zoom into your statistic. There we go. All right. So I want to put the equation of the regression line on there. I want a line on that graph. So I could draw a line if I want to. I can go take my drawing tool and go, okay, I want to put a line on here. Oh, it won't let me put a line on there. Never mind. But I want the equation of the line, so I'm going to press y equals. And I'm going to put the equation negative 42.1 plus 0.133x. And x is up here, xt theta n. So now here comes the line. I got the line on there. So the points, the farther the points are away from the line, the larger the standard deviation. Now I came up with standard deviations for x, standard deviations for y. Those values are in the x direction and the y direction. But there's an S. S stands for standard deviation of the residuals. So how far away are these points from the line? How far away are the points from the line? So the farther away the points are from the line, the larger the residual. Okay, so we want points close to the line in order for it to be linear. I'm going to graph a couple more things on there. I'm going to graph the mean of y and the mean of x. Press y equals. The mean of y is 25. Y bar is 25. Okay, I've been doing this the whole time and you guys can't see it? Okay. Okay. There we go. That was funny. I can see it. You can't see it. Automatically. It was on the screen. Alright, so I put the equation of the line in to the calculator. And then I press graph. And the blue line is the regression line. The least squares regression line. The red line is the mean of y. The mean of y was 25. I'm going to put one more line on there. I'm going to quit that screen and I'm going to draw a vertical line. So here's the drawing feature. We can't draw vertical lines on our calculator with y equals. We have to use the draw feature. Second program. We can draw all these types of lines. We could draw circles. So I'm going to go to vertical, number 4. Draw a vertical line, and the vertical line was 506.4. 506.4. That's not 506. Oh my gosh. Number 4 is vertical. 506.4. Press enter and it'll draw on the graph. So there's the vertical line. Notice that this is the mean of x, this is the mean of y, and the two lines intersect. The two lines intersect on the predicted line, the regression line. So that's kind of an important point, that x bar and y bar are actually numbers on the line. So the standard deviation of x is how far each of these points are from, on average, away from the blue line, the vertical line. Standard deviation of y is how far away are these points from the red line. Okay, how far away are those points from the red line? And then S, your standard error of the residuals, is how far away are the points from the predicted line. I tried to draw on there. Well, let me draw now. Kinda. Oh, I'm drawing a white line, that's why. Can't see it. Okay, there we go. Okay, this distance right here is called a residual. The distance the points are from the predicted line. And the predicted line is y hat. This is y bar. There's a difference. Y bar is the average, and y bar was 25. So the distance those points are from the line, I'll use a different color, I'll use yellow. This distance from these points to y bar is called your average difference. All those yellow lines, that would give us S of y, standard deviation of y. And you're not going to have to ever calculate these things. You're not going to have to calculate them using your calculator. You will just need to know what they are. The standard deviation of x is how far the points are away from the x-axis. Whoa, that was a terrible line. Not the x-axis, I'm sorry. The mean of x. So how far away are those points on average? So it's always an average. Standard deviation is the average difference. All right. So that's percentage graphing in a nutshell. We'll go back to this screen. A lot of information. That's just giving you the answers to all those things that we just did. Writing a regression equation. Okay, so we're going to write the equation using all these statistics that we were given. So given a correlation of 0.8, standard deviation is 3, standard deviation of x is 4, x bar is 7, y bar is 10. Given those things, we can write the equation of the line. Now, if you're following along in the textbook, this is page 172 and 173. How to write a regression equation. It's going to feel like we're going to jump through a lot of stuff, and then I'll bring it all together at the end. But this is finding the regression equation. So we're going to take the information and we're going to plug it into an equation. B equals R times S of y over S of x. So typically we'll see it written as a fraction. I don't like the slash mark. I don't know why I put it on there. I should have done a fraction like this. So we plug it in. R is 0.8. S of y is 3. S of x is 4. 0.8 times 3 divided by 4 is 0.6. And then A is your y-intercept. And in interpreting the y-intercept, we don't really have, we can interpret the y-intercept like with the manatee data, the y-intercept was negative 42. When x is 0, predicted y is going to be negative 42. Okay, the y-intercept doesn't have a practical meaning, so we don't usually interpret the y-intercept. But we need to know how to find it. So I'm going to find the equation on the line for the manatee data using this. Here's the equation given these statistics. So the manatee data, R was 0.937. And the standard deviation of y, I wrote it down, standard deviation of y is 8.7. Because I did two variable statistics for list 1 and list 2, and that's where I get this information. S of x is 61.7. So I plug that in. Oops, I gave you the wrong thing. This is B. Having a day here. B equals, okay, R is 0.937, and I'm going to do that calculation now. 0.937 times 8.7 divide 61.7. 0.132. I think the original number was 0.1326. I rounded up to 1.133, but I have rounding error here. It wasn't actually 8.7. The standard deviation was much larger than that. Okay, and then the slope of the line is interpreted as rise over run. Okay, and you think of there's y and there's x. So that helps us come up with the interpretation as well. The average of y is 25 minus b. So we had to calculate b first. B always gets calculated first because we use the slope to get the y-intercept. So we plot a point. A point is 25 and 506.4. That point is on the graph. And then we go backwards to find the y-intercept. This is a mathematical thing. So I could just punch it in just like that. 25, take away 0.13 times 506.4. Negative 40.8. So it's off slightly again. It was negative 40.2 or negative 40.1. I forgot what it was. I got negative 40.8 for that y-intercept. So that's calculating the slope and the y-intercept for a regression equation given statistics. So we'll have an opportunity to do that one again a little bit later. A couple other things. We got to interpret the correlation coefficient. We got to find the residuals. Okay. So what's a residual? Use the word residue. In the word residual is the word residue. If there's residue, that's leftovers. For example, when I erase my whiteboard, there's little dots of marker that fall out and it gets all over my hands. That's why I don't wear a white shirt, because it gets all over my white shirt. That's residue. It's leftovers. Okay, or I put my cup down of water, and then the ring of water is on the table, and then you put your paper on it, and then your paper gets all wet, and you're like, oh man, I hate it when I do that. That's residue. So residuals are the leftovers. So I got to plug in. What I did here was I plugged in 447 into the regression equation. I plugged in 460 into the regression equation. Plug in 481, 559, and 585. Plug all the numbers into the equation. And I think we could do it on our calculator, plugging the numbers in to figure out these predicted values, where they come from. I'm trying to think if I could do it on my calculator. Let me check my calculator. I think I got a trick for this. Y3 equals negative 42.1 plus my slope 0.1326 and then x. Okay, so times x. But all my x values are in list 1, so I'm going to put L1 here. This is like a trick to find. This is all of the predicted y values. And the difference between the actual values, list 2 is my actual values, list 3 are all my predicted values. So I just plugged in every number into the predicted values. I could also do that with my calculator. So I did that already. Negative 42.1 plus 0.1326 times, pick a number. What was it, 461? I'm going to do the first one. 447 times 447. 17.17. 17.17. It's pretty close to 17.
You can't see your calculator.
Oh my gosh, I did it again. Stop share. Okay, let me stop sharing my screen. I thought I shared it. Okay, I just plugged in 447 in there. I just plugged in 447 into the calculator. I found the residuals in list 3, or the predicted values in list 3. I'll do it again since you guys didn't see it. Highlight L3, press enter, and then I'm going to plug in negative 42.1 plus 0.1326, and then all my x values are in list 1, so I'm going to put L1 here. So I found all the predicted values. So 17.172, that's what I got when I calculated it. 17.172, the first predicted value is 17.172. I just did it all in the list. I plugged in all the numbers, so these are all my predicted values. 17, 18, 21, 32, 35. That's what you see on the Nearpod. 17, 18, 21, 32, 35. Those numbers are all right here, except these numbers are off slightly. I think I used what did I use there? I think I used 0.13 instead of 0.1326. So that's why the numbers are off slightly. Then define the residual. To find the residual, you subtract the residual is y minus y hat. Actual value minus predicted value. So in order to find a residual, you take your actual value and subtract the predicted value. These are the leftovers, the residuals. The difference between the point and the line. Okay, and we want to make a residual plot to see how off our predictions are. So down here at the bottom row is our residuals. -3, 3.3, 3.6, 3.4, and -1. I subtract the first row with the third row. 33 minus 34 is -1. 34 minus 30.6, -3.4. So I have to do that 5 times in order to find the residuals. Okay, now I can share my calculator. Hey, the good thing is when you go back and watch this video, you'll be able to see all the calculator stuff that I've been doing. You'll get to see it twice. All right, list 4. I'm going to, whenever we do lin reg a plus bx, so if I go stat, calculate number 8, and my x list is list 1, my y list is list 2, calculate. There's my a. Yeah, -42.1. It's actually pretty close to -42.2, so that's a rounding error. 0.1326. R squared is 0.87. We'll get to R squared in a sec. And then R is 0.937. Whenever I do this, a residual graph is made. The residuals are calculated. So if I press second stat, notice there's a list called residual list. If I go down to the residual list, I can see what those numbers are. Just press enter. -4.1, 2.15. I'm using the arrow key. 2.326. 2.02. And the last one is -2.4. It's kind of hard to read like that because it goes out to 8 decimal places. So I'm going to put them in the list. So press stat, enter. I'm going to highlight L4. L4 is highlighted. Press enter. And I'm going to put that name up there. So second stat. And number 8 is residual. List residual. There's all my residuals. Just like I had on the Nearpod, where I subtracted list 2 and list 3. If I subtract list 2 and list 3, I should get these numbers about. I could actually do that. List 5. I'm going to do list 2 minus list 3. L2 take away L3. Should give us pretty similar numbers. Pretty darn close. I just got some rounding error there. I'm going to make a graph of the residuals. It's called a residual plot. And the reason why we would do this, we want to say, is there a relationship between the two variables? So a residual plot, how well tells us how well the line fits the data. This is page 174 and 175. Making a residual plot. How well the line fits the data. Residual plot. So they got a scatter plot there on page 175. The residual plot is next to it. So if we have good scatter on our residual plot, the points are just all around the line, then we can say that the line's a good fit. Reminder of the graph. Okay, so the points are, 3 points are above the line, 2 points are below the line. So how far away are these points from the line? What we do is we take that line, that regression equation line, and we straighten it out. Kind of flatten it out. So I'm going to get rid of the y bar. And I want to make the residual plot. So second stat plot, and plot is on already. I want to graph list 1 versus list resid number 8. And then graph, well, I got to zoom 9. There's a residual plot. So I took that last list that we just created and made a plot of that. So you can see the plot, the residual plot. The vertical axis is your residuals. The horizontal axis is your x-axis. So the definition, a residual plot is a scatter plot of the residuals against the explanatory variable, against x. Residual plots help us assess how a regression line fits the data. So residuals help us assess the goodness of fit. Is it a good fit? Is it linear? Okay, if there's good spread, then your line is linear. Let me give you an example of something that's not linear. So let me do a graph. Now I'm just going to put a scatter plot on here. Is that linear? Okay, and the answer is pretty obvious. The answer is no, it's not linear. So if I graph a residual plot, and I put a line on there, wow, my line's terrible. I knew I should have done this. Okay, put a line on there. You'd get like R is 0.9 or something like that. But if you look at the residual plot, the first point's above the graph, second point's near the graph, third point's below the graph, and then below again. There's some kind of curve there. So if there's a pattern in a residual plot, then we know the data is not linear. We know the line does not fit the data well. If it's not linear and the line does not fit, then we cannot use linear regression. We can't make predictions for this data set. All right. R squared. So let's look at R squared. One thing you want to look at is the residual plot. Another thing you want to look at is R squared. R squared tells us how well the line fits the data. It tells us, just like the residual plot, it's on page 179. How well does the line fit? Look at R squared. Since R squared is 0.878, we can interpret R squared. R squared is called the coefficient of determination. R squared gives us the percent of variation in the y values in terms of the least squares regression line. Or again, like I said, how well the line fits the data. So this number is interpreted as a percentage. 0.8 is pretty close to 0.88. So if we're going to interpret that, we would say 88% of the variation in y can be explained by the least squares regression line. So they would sometimes interpret it as the percent of variation that's explained variation, and 12% is unexplained. So it's always out of 100%. There's LSRL again, least squares regression line. 12% is unexplained. It also continues of y on x. So you could use a template for of y on x. Least squares regression of y of the number of manatees killed on the number of on x. Alright, so that's interpreting r squared for this case. Interpret r squared. So this is a big picture thing. We could just look at r. We can look at the correlation coefficient, but that's not enough. Correlation coefficient only gives us one thing. So we look at r squared. We look at making our prediction. So is our prediction accurate is the ultimate goal. If r is strong correlation, if r squared is high, if we have a scatter plot that shows a good fit, we want to state that we can make good predictions. Then there's S. So standard deviation of the residuals is S. Not S of x or S of y. There's 3 standard deviations when you are calculating least squares regression. Page 177. Page 177, standard deviation of the residuals. Standard deviation of the residual squared is n minus 2. And notice it's y minus y hat. So your actual value minus your predicted value squared divided by n minus 2. That is like standard deviation of x or standard deviation of y. Standard deviation of x is x minus x bar. Standard deviation of y is y minus y bar. Standard deviation of the residuals, also called the standard error, or just S. If you're ever given S, then you could find the standard deviation. How far away are the points from the line? The average distance away from the line. Or the average difference of the distance away from the line. And it says right there on page 177, this value gives the approximate size of a typical or average prediction error. So if we have a large standard deviation, we have a lot of error. Okay. We have small standard deviation, we have small error. A lot of information here. So we're going to investigate all these things right now. Standard deviation doesn't come up that much, but calculating standard deviation of S, you have to do a linear regression t-test to find S usually, or you can calculate it. I'm going to do it on the calculator real quick, just in case. So it said to square the residuals. So remember, I have my residuals in list 3, or list 4. So I'm going to square those numbers. I'm going to do that in list 5. Square the residuals, and then add them all up. So I'm going to do list 4 squared. So list 5 is equal to list 4 squared. So there I squared all the numbers. And notice they're positive. Some residuals are negative, some are positive. Standard deviation is always a positive number. We square, and then we square root. So I got to do the sum of list 5. Second stat. Go to math. Sum L5. Alright, and then I got to divide by n minus 2 in the equation. Okay, n is 5. There are 5 years of data collected. So 5 minus 2 is 3. Divide by 3. So I did sum divided by n minus 2, and then I got to square root that answer. Standard deviation is 3.5. That's S. Okay, again, smaller standard deviation means small spread. Okay. I don't think you'll have to do that anytime soon. So most of it's going to be interpreting R squared, finding R squared, making a residual plot, interpreting the residual plot. Is there a correlation between two variables? So let's interpret the slope of the line. Enrollment at Santa Maria High School has increased annually from 2000 to 2007. The least squares regression line was given. What are explanatory and response variables? What explains the other value? So years is in X, and Y is the number of students. The enrollment means number of students. So X is years, Y is number of students. Interpret the slope of the line. So again, slope is 56.37. We predict, or a predicted average increase of 56.37 students per year. Or as each year increases, we predict an increase of 56 students. So in 2007, there were 2,000 students. In 2008, there are 2,050 students. In 2009, there are 2,100 students. We increased by about 50 each year. It's an average increase. Or they use the word typical increase as well. Make a prediction. What is the population of the school in 2008? Make a prediction. So I'm going to use the equation to make the predicted value. Negative 110,608.76 plus 56.37 times 2008. So I'll just punch that number into my calculator just as you see it. Negative 110,608 56.37 times 2008. 2582. So we predict an increase of 56 students from 2007 to 2008. In 2008, we predict 2,582 students in the school. And that sounds right. If you get a number like 10,000, oh, we predict there's going to be 10,000 students in our school, then that would be way off. Okay, is the prediction accurate? Probably not. If you underpredict, like negative, you get a negative number, under prediction. If your school population is decreasing, you get negative values. But the ultimate question here is the prediction accurate? Well, again, we got to look at R squared. We got to look at a scatter plot. We look at R. We got to look at S, standard deviation of the residuals, to calculate and make these decisions. But 2008 is outside the data set. Okay, we have data from 2000 to 2007. So if we predict outside of the data set, that's called extrapolation. Okay, but not really. I mean, if you predict what's going to happen next year, you're not really extrapolating too far in it. But if you said, what's population going to be in 2020? Then 2020, we got, oh, there's going to be 6,000 students in 2020. That's really extrapolating. All right, coefficient of determination, R squared. A little bit more about R squared. Okay, so again, we kind of brush through that real quick, but this is the definition. Again, the definition, how well the line fits the data, the role of R squared in regression. Coefficient of determination. That definition is at the bottom of page 180. fraction of variation in the values of y that is explained by the least squares regression line of y on x. Okay. Sometimes we could leave out that last part. So if this last part is extra information because we're already saying the fraction of variation is a percentage. So fraction of variation just means fraction. Fraction is a percent. Usually we write it as a percentage. Fraction, ratio, percent, all are equivalent. So here's an example. Might be kind of a confusing example because there's percentages for percentages. Some people think that the stock market in January will predict the stock market the rest of the year. So people that invest in the stock market, they're trying to make money. Okay, it's legal gambling. They invest money, but if they see what happens in January, they're like, oh, this stock's gaining money in January. Therefore, it should gain for the rest of the year, so I'm going to invest. So there's a correlation between the two. The correlation is 0.1596 or 0.596. There's a correlation. What percent of the observed variation in yearly changes in the index is explained by a straight line relationship with the change during January? That's a fancy way of saying find the coefficient of determination, r squared. So if you know r, find r squared. I might need to give you some background knowledge. If you know r, if r equals 4, what is r squared? Okay, square 4. Thank you. All right. Woohoo! Oh, Dallas is here. Square it. Same thing. If you know r squared, if r squared is, let's use a cool number, 25. If r squared is 25, how do we get r? We would square root 25. So to go from r to r squared, we just square the value. To go from r squared to r, we square root the value. Okay. All right, so in this problem, it says what percent of the observed variation in yearly changes in the index, yearly index, is explained by straight line relationship. So if we got r is 0.596, we're going to square that. 596 squared, calculator, 0.35. %35 of the variation in yearly changes in the index is explained by the least squares regression line. It says straight line relationship, but that's LSRL. So whenever you're given a question like this, again, you're going to parrot the question, you're going to write it in context. What is the equation of the least squares regression line? Okay, so now we got to use our knowledge of slope and y-intercept. I gave it to you down here. I gave you the equation, but you got to use your knowledge of slope and y-intercept to come up with the equation of the regression line. So we got x bar, we got y bar, we got sx, we got sy. So let's find the equation of the line. So here it is again. This is going back to the beginning, so I'm kind of going through. This is a typical problem that you'd see. You'd have to do 3 different things for one set of statistics. So r is 0.596. Standard deviation of y, 9.07. Standard deviation of x, 1.75. Do the math. Okay, and I just punch in my calculator 0.596 times. So on my calculator inputs 0.596 star. Okay, times on the calculator is a star. 9.07. And then we go in any order, multiplication and division, slash 1.75. So this means divide. So if I just punch those in, I should get 6.083. That's B. A is the y-intercept. So y bar 9.07 minus B, which we just found, 6.083. 6.083. And times x bar, which is 1.75. And again, we should get 1.707 when we do that calculation. Then make a prediction. If x bar is 1.75, oh no, not x bar. If x is 1.75, just plug in 1.75 into the regression equation. So we got the regression equation, plug in 1.75 into the equation. So it'd be y predicted value is 6.083 plus 1.707 and then 1.75. That would give you a predicted value, y hat. So that's making predictions. Plug in the numbers, formulas, stuff like that. GPA and IQ was given. Okay, we have x bar, we have y bar, we have s of x, we have s of I, we have r. What are responsive explanatory variables? So x is IQ. IQ is 108. What percent of the observed variation in these students' GPAs can be explained by a linear relationship between GPA and IQ? Blah, 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 blah. Okay. R squared. That's interpreting R squared. So again, 0.6337. 0.6337 squared. 0.4. 0.40. 40% of the observed says what percent? What percent? So that's 40%. 40% of the observed variation in students' GPAs can be explained by IQ. Not very good. Not very high. Write an equation. Write an equation. So again, we're going to have to plug in, S of y, 2.1 times 0.6337 divided by 13.17. So that's finding the equation. 0.6337 times 2.1 divided by 13.17. 0.101. So find the equation. I got B is 0.101. $7.447 minus 0.101 times 108.9. Negative 3.5. And 1.101 was positive, so I put a plus there. So I went through that really fast. I know we're running out of time already. So I still got a lot more stuff to talk about. Ecologists found that areas with large beaver populations have a strong correlation with the amount of beetle larvae in tree stumps that have been cut by beavers. The correlation coefficient is 0.94. Interpret R squared. So again, this one is going from R to R squared. So how do you go from r to r squared? We square it. And you get, it's actually 88%. I think that's the wrong number there. Should be 88%. So if you square 0.94, get 0.88. 80% of the variation in the number of beetle larvae is accounted for by a linear relationship between the two values. This one is correlation coefficient. So you're given R is 0.8. R is 0.8. The score is before the final exam and after the final exam. The professor wants to use Gina's score to make a prediction. Oh, what would you have gotten on the final? Well, if R is 0.8, only 64% of the variability in final exam scores is accounted for by a linear relationship with pre-exam totals. So if I'm going to make a prediction with this data set, I probably would not have accurate results. So argue for Gina that her grade should be higher or lower based on what you know. Okay, this is not an accurate prediction because 64% variability, there's a lot of variation from one score to the next. This is an example of a problem where you got to make predictions. Lap time in the swimming pool and pulse rate. So you think the faster you swim, the higher your pulse rate. So if we make predictions far outside the data set, like if your lap time is 120, that's called extrapolating. Interpolating is predicting inside the data set. Write an equation on the line. So again, we would put the data into list 1, put pulse rate data into list 2, and then write a least squares regression equation by getting A, B, R squared, and R. We don't have time for all of these. A study showed that students who spend more time studying for a statistics test tend to achieve better test scores. In fact, the number of hours studied turned out to explain 81% of the observed variation in test scores among students who participated in the study. So 81% of the observed variations, that's R squared. What's correlation? Well, this is going backwards. We go from R squared to R. Go backwards. So I talked about lurking variables for a minute. A variable that is not among the explanatory response variables is called lurking variable. So here's an example of lurking variables. Since 1860, the number of Methodist ministers in New England has increased with the amount of rum that has increased or been imported. R is 0.999997. What's the lurking variable? R, there's a strong correlation between the two. So that means all the ministers are drinking rum. Well, not really. Ministers don't drink rum. They're religious people. Most of them don't drink. But what's the lurking variable in this case? It's population. So we think that the ministers are causing Z, X causes Y. Okay. The number of ministers is X causes the amount of rum imported. But that's called causation. Okay. X does not cause Y. Even though R is high, we probably have a really good scatter plot. We have a linear relationship. We look at the residual plot. Oh, there's good scatter. We do all these things, but we got to think logically about data. There's a third factor, Z, that affects X and Y, and that's population. The population, so Z is population. As population increases during those times, so as the number of ministers, so as the amount of rum that has been imported. So we have a lurking variable. And sometimes you'll see it's causal. We'll get to that in our next chapter. We don't have time for this, but this was doing the same thing, studying the relationship between X and Y and getting R. For all of these, R and R squared are really high, but some of them are not linear. So we cannot use linear regression. We cannot use linear regression if the scatter plot is not linear. So the first thing you want to do when you get data is make a scatter plot. Is it linear? You want to look at R squared. Is there a high percentage of variation between the two variables? The one thing I left off was on page 182. It's looking at scatter plots, looking at Mini-tab printouts. So computer printouts, take a look at that. Read through page 182. It's real quick reading. But looking at a mini-tab printout, how to get the standard error, how to get the slope and the y-intercept. And the bell rang. So make sure you do the quiz 3.1. It's only 8 questions, 4 points for describing your data set. So that's it for today. Thanks for participating. Watch for the video. I'm going to email it to you. Look at your email if you want to see this video again. All right? So have a great day. I hope to see you soon. Have a good week. Thanks. You too. And goodbye.